Okay, hello everyone, and welcome to the first domain introduction sessions by ERC. So broadly in this session, we will be going over the three main domains that ERC and the projects in ERC involve. That is electronics, mechanical design, and automation. So I'll be going first, and we will start with an introduction to electronics. So, yeah, before I begin, I am Atharva. I am in my second year and I am a core member of the ERC. And just to give a sort of a start, my journey with electronics also started when I got into the club in my first year. Before that, even I did not have much exposure to electronics. So, with that background, and today I'm taking this introduction session. So, this is the point of saying is that even if you are not acquainted with electronics, this is the right place. You have come to the right place and you can get a great start here. Okay, so let's just go over what all this session will cover, right? So the first and most important question, that is, what is electronics, right? The second one is a important question, which is, why does it matter, right? Because if you're doing something, then you should know why it makes a difference. Then we'll also cover where ERC comes into this, how ERC and electronics are related, because as you know, the E in ERC is electronics. So we'll cover that. And finally, what's in it for you and how you can get started on this journey. So that is what we'll be covering in this session. Okay. So what is electronics, right? You have Most of you, or rather all of you, have studied some basic electronics in 11th and 12th, and so you must be knowing that electronics is related to electrons, as it's clearly there in the word. And so in extremely simple terms, it is the study of motion and manipulation of electrons, right? So yeah, there are many electronic devices, that the basics ones that you've studied might be resistors, inductors, capacitors, and then you can build a lot of interesting and useful circuits using those. And all of those devices at the very root level are doing some sort of manipulation of electrons and thereby energy, and you are creating some sort of a good output, and you're trying to do something useful. So that's what basically, in a very broad sense, what electronics is. And as you start upon this journey, you will dive deeper into how things work and how you can use the knowledge of electronics to make some great applications in robotics too. Okay, so now an even more important question: why does it matter, right? Like, why do we care about electronics, or why is everyone talking about electronics? The reason about that is, there are two main reasons I feel. The first of them is that a lot of the energy that we use today is in the form of electricity. So in, let's say, a few thousand years ago, when there was absolutely no form of electricity available to man, things were more mechanical. So your systems were more based on mechanisms, and energy sources might have been something like fire or even animals or labor or something like that. But in today's world, the major source of energy is electricity, and in order to manipulate and use that in a good way, you need to have an understanding of electronics. And similarly, we are living in the age of the internet, in the age of, we call it a digital age, right? So, and that is because most of our information, most of our data is in the form of some or the other electronic signals. Like when things are stored in your computer, in your memory, that is nothing but they are, so you're aware of binary, right? So that is nothing but of variations in signals that we have given some meaning to, and we interpret them as whatever information we want to. So these are the two main reasons why electronics in today's world really matters. And that's why studying that and getting into it will help you into building something useful, right? So it's important to think about that while you are approaching, because if you know why you're doing something, then you're much more likely to be interested, and it's going to be a much easier ride for you. Okay, so we'll start with a very small example and a very basic example. You don't need to know about the details about all of this work. We'll just go through it and understand what levels electronics is involved in. So let's say you have a temperature sensor based heater. So you have a mechanism where you want to maintain the temperature of your room, right? So for that you will need two things. The first thing you will need is you need to have something that will measure the temperature, right? Because you want to maintain it at some certain level. And then you need a second mechanism which will be able to give an input to the environment such that the temperature can be varied. So something that will heat up the environment or something that will cool down the environment, right? So as you can see in this diagram, you have so you'll take in an input from the environment, right, in the form of heat transfer, because you have learned in 11th and 12th that whenever there is a gradient of temperature, there is a flow of heat across it, right? So you'll have some sort of heat transfer into a sensor, right, which will tell you what the ambient temperature is. Then you will feed that information into a circuit. You'll process it using some or the other technique. Then that processed information will give you something as an output, and that will be what you need to do by reading the temperature, because you want to maintain it at certain level. After that, you will that circuit will receive this information, and it will, one of the very rudimentary ways of changing temperature is to heat an electric is to basically pass a current through a coil, which then gets heated, right? Even this is something you've learned in 11th and 12th. So you'll that circuit will control a current through some coil, which will eventually lead to a temperature change in the world. And then this cycle just continues, right? So let's have a look at this in a bit more detail. So now let's try to think about what this sensor might be doing, right? So you have a change in temperature. There is going to be some mechanical change in the sensor. For example, change in resistance, right? Even this thing was covered. So I'm trying to make this example off of what you have learned in 11th and 12th, so that it's not too complicated. Might be that the real sensors would not work this way, but this is just to give you an idea about how a thinking approach might be. So then there will be some change in the resistance because of an increase or decrease in temperature, right? Because of heat transfer. Then due to this, then there will be a variation in the voltage across that particular resistor, right? And then when you can measure that and you can give out an output current to your circuit, which will then change what amount of current is going in that coil. So as you can see, we have started with some mechanical change. We have found a way to convert it into an electrical signal, and then we have used our knowledge of electronics and different devices in electronics to process it and then produce another mechanical change eventually, right? So that is just to give you a sort of overview. And now the next important question is that where does ERC come into this, right? So obviously ERC doesn't make heaters, but what we do is the work is mostly divided into these three domains, right? You might have heard of these domains from some of your seniors or in general if you're interested. So they're broadly analog electronics, digital electronics, and PCB design. Now electronics is much more than just these three domains, right? But because we are electronics and robotics club, we don't focus into how exactly a particular electronic device works. Although the core of electronics also lies in that as well. What we do is we try and take the constructed electronic devices and we try to use them in our applications and in our robots such that we are able to achieve something useful, right? So these are just three domains that the ERC works in. Electronics is so this is just a subset of what the entire electronics domain is, right? So we'll just quickly go over each one of them. Right. So analog electronics. You must have heard of this word definitely, I'm sure. So basically, they have systems that deal with continuous signals. Like, so we all know that you have an analog watch as against a digital watch, right? So the second hand in an analog watch, usually it moves continuously, it moves smoothly, right? It doesn't stop at every 1 second. So technically it is taking the value of every second between 0 and 60, and it's not stopping discretely at any point. Similarly, you when you have continuous signals, that is basically analog electronics. And majorly the use cases of this are in sensors and applications that have to do with audio and radios. So let's just go over. I'm trying to just introduce you to the names of a few. It's obviously all right if you're not aware of any of these, because even in my first year I was seeing these terms for the first time. This is just to get you an overview of what all is there and what all you can explore. So a very crucial part of analog electronics is what is called as an operational amplifier, which is basically it can take in an input as a current or a voltage and then amplify it or scale it basically to output a value of whatever voltage or current that you require. So you'll learn about this in your second year if you are under the EEE department. But even if you are interested in electronics, operational amplifiers are one of the most heavily used devices. Then there are also things that are called as filters. So maybe you have studied some of these in your 11th and 12th. So this is a diagram of a filter, which basically, so a filter is, you know what a filter intuitively means, right? So it's going to allow some things to pass ahead and it's going to block some things. So like here, this example here shows a low pass filter. So what a low pass filter does is it's going to allow only signals of up to a particular frequency to pass through, to be available at this output, and the others will be blocked, right? And similarly, you have two very important transforms that are not just important in electronics but all across engineering, and that is the Fourier and Laplace transforms. Okay, and even these you will be learning about in over the course of your engineering. They're basically used to convert from the time domain to the frequency domain. Now, it's fine if you don't understand what this means. You can watch a few videos about them, or you can explore and learn more. I'm just trying to introduce a few terms to you and just to get you interested. But just note that these are very important and they are heavily used in engineering in general. Okay, so that was about analog electronics. Uh, Next up is digital electronics. So again, we'll use the same example as the watch. Like you have a digital watch that shows you discrete seconds. So so the watch is going to stop at 1 second, then at 2 seconds, then at 3 seconds. You'll never find it at 2.5 seconds, right? So that is basically digital, where you have discrete signals. You have specified levels from which you transition directly. You don't stop in between those levels. Your signals transition between them directly. And then the very common notion of binary and usage of zeros and ones, upon which digital electronics heavily relies upon, is basically you have a high voltage or you have a low voltage, and those are the only two values in which your device operates, right? So yeah, another part of a very rather important part of digital electronics that ERC works in mainly is microcontroller programming. So you might have heard of this board, which is known as an Arduino board. Many people who are starting out in electronics are usually start out their projects using an Arduino board. So that's basically a very small computer on a single chip. So as you can see here, this black chip over here, that's an integrated circuit. It is the Atmega IC, and that basically has processing power to a very small scale compared to your computer, but it has stuff like a CPU. It has input and output pins. So the black headers that you're seeing over here, they are the pins which you can use to input and output signals. It has some memory, it has processing, and it's basically like a extremely small version of a computer. And for certain small scale applications, these microcontrollers are very useful. So you'll mostly be starting out with using an Arduino or maybe an ESP or a Raspberry Pi. So that was about microcontroller programming. Yeah, and to PCB design, right? So PCB stands for a printed circuit board. Maybe some of you have heard of this before. So what a PCB does is basically you have different elements on your circuit. You have different devices. You have different connections. You have connections to different sensors. You have certain, let's say you have some motors. You have something that brings about a change in your environment that is called as an actuator. So basically you have different connections, and you want to get all of them on one piece in a compact way, in the most efficient way possible, so that you reduce size as well as costs. So that is where PCB designing comes in. So you organize, as you can see here, so all of these are pins. So this is basically a schematic of a PCB that is drawn, and there are softwares available for this, such as EagleCAD or by Autodesk, and you can basically design. You can have a layout, you can have structures, you can make connections, and then you can send such a design like this to print. So you have fabrication labs where you can you have PCB manufacturers where you can send your designs, and then you'll get a board printed. So this is a schematic for an Arduino, and then as you can see the connections that are, like, you can see connections are made over here between the pins as we had designed. So this is also a very crucial component of making an actual working prototype or making a device, because you want to get all of your circuit organized properly so that there are no loose connections, and you want to fit it in the smallest space possible. That is where PCB design comes in. Okay, so just a quick example as to how these three things are integrated into one single thing at ERC. So this image that you're seeing, this is Trotbot. This is one of the oldest projects of ERC that has been started by our super seniors. And the main goal of this project is to make an autonomous indoor navigation and delivery robot. So as you can see, there is space over here to put something that you want to deliver, and this is the part where the electronics goes. So it has a microcontroller, it has an Arduino at this point, and it has an onboard computer, which is the NVIDIA Jetson Nano. So they are all parts of digital electronics. Then this black thing that you see over here, that is a LiDAR sensor, which basically gives you a reading of how far around you obstacles are. So that is basically one of the tools used for detecting and avoiding obstacles. So that is a sensor, and that comes under analog. And as you can see here, this is an old picture. So here you can see two, three things are mounted, right? So we're working on a custom PCB to integrate all of this. This is the battery, this is a power bank. So we're trying to integrate all of this into one single PCB, and we will soon be sending that to manufacturing. So work on that is currently going on. Okay, so that was quite a long thing, and it might feel like too much information. And the reason for that is, some of like quite a lot of this might be new for you at this point, and that's completely fine, because you're in first year. Even for me, all of this I've learned in over the course of the last 1.5 years. So then what do you do, right? So if any of this seems even remotely interesting to you, then ERC is just the place to be. You can start exploring. We have a lot of opportunities coming up at ERC. So we'll go over how you can get started. So we have a thing which is called as the ERC handbook, which is a exhaustive, like it's an extensive collection of resources across all domains related to robotics. So you can have a look at that. It has a roadmap about how to get started. It gives you descriptions of things, and also gives you links to a wide number of resources. So you can go and check it out. Another source can be QSTP materials. So QSTP is Quark Summer Technical Projects. You'll get introduced to this in your after your first year during the summer break, if you have it this time. But that's basically an initiative by Quark that, and we have usually we have 2 or 3 QSTPs every year from ERC. One of them is mechatronics. So there are also resources linked here. You can have a look at them. And finally, we have mini projects. So as you must be knowing, if you've attended this earlier session, where inductions are going to be conducted through mini projects. So we'll have to select one or the other projects, and based on the work that you do there, based on your interests, you will be inducted. So we'll be making the announcement about mini projects soon. So stay tuned. The best way I feel to start is using these resources in one of your mini projects, because that is how I got started. And I don't think I could have done anything better at that point. So stay tuned for that. And in case you're interested in Arduino, Jeremy Blum is a YouTube channel where you can find a good tutorial on how to get started physically. If you have an Arduino at home, or if you're willing to buy one and try things out, you can check that out. So we have linked all of these links and even further links from mechanical and automation in this QR code. You can take a screenshot of this, or you can have a like you can pause and scan this QR code, and you'll be able to see a page that has all of these links. Yeah. Okay, so we'll FAQs. I'm sure these questions might be going through a lot of your minds, and that's because even I was a firstie 1 year ago, so I had all of these questions as well. So I have, let's say you have not worked with electronics before. Is that okay? That is perfectly fine, because most of us, like a lot of us, have not worked on something big before coming to college, and that is why we are in college now. This is the place where you can get started, you can explore, and ERC is a great place to start that. Then, is electronics difficult? So I feel that this is an opinion and this is not information, but like I think it is subjective. I'll definitely say that it is vast. Electronics is vast. It has a lot of domains. It has lot of depth, and you'll really need to understand stuff if you want to make something. But at the same time, that journey is extremely interesting and it's very rewarding. So if you have any assumptions in your mind that electronics is difficult, or if people have told you that, then I feel that it is best to decide for yourself what you think about that. Yeah, so don't go with any biases in your mind that it's difficult or something like that. Yeah. And another thing is that I don't know any programming language, so what do I start with? So if you're interested in electronics, the best thing to start with would be C or C++, because Arduinos and some microcontrollers are coded using C++, and even a knowledge of C is enough for that. Yeah. So that is basically what you can start with. We'll also attach a link to the resources for learning that in the sheet that we mentioned. Okay, so questions. You can type your questions in the chat. If I've already covered your question, then it's fine if you don't put it again. I'll wait for a while for the questions. Okay, so there's one question. I think it might also be a FAQ. I should have put that in there. Is that being from an electrical branch, does that matter here? So no, it does not matter. What will happen is that if you're learning electronics, you'll also have that as a part of your courses. So if you're interested, if you're working on electronics in ERC, you'll also have some electronics based courses as a part of your college. But even if you're not from electronics, that does not mean in like that in any way, that does not mean that you cannot participate in ERC electronics activities. It is like irrespective of your branch, it is only up to your interest and only up to how much effort you put in. So electronic students do not have any advantage or disadvantage over any other people. Whatever branch you are from, you are most welcome to try out. You should explore and find your interests, and then you'll find a way. So no, electrical branch does not make much of a difference here. Okay, so okay, about the inductions. Okay, so basically what the induction format is going to be is that after today's session, we'll have another session wherein we'll talk about mini projects, right? So we will have two or three projects from every domain, that is electronics, mechanical design, and automation, and you can select any one of them, and they will be basically starting right from scratch. You will not have to have any, though we won't have any prerequisites. This is because it's meant for learners, it's meant for beginners, and then you work your way up through that. You learn, you interact with us. So we'll have sessions every week to check your updates on the progress, to check your basically all you have been doing in the projects. And after that, there'll be a final submission after around 5 or 6 weeks, and based on that, then the inductions will take place. But let me assure you about one thing, that if you participate actively in the mini projects, and if we see that you are willing to learn, then that is more than enough to get inducted. So you don't have to worry about things like how many people are inducted, or is there any exam, or is there any test, something like that. That's not what we are looking for. All we need is you to show interest and you to be willing to learn and work hard. That's it. Okay. Any more questions? I'll wait for a few seconds if there are any more questions. Okay, so can we do more than one mini project? Yes, definitely you can. In fact, you can even choose mini projects from across domains. And there will be a detailed session about mini projects after this is over. So we will cover all of those details in that session properly. And in that session, you'll also be explained about every mini project in detail, what the goal is, what you will get to learn, and where it is applied. So don't worry too much about mini projects right now. There will be a separate session for that where everything will be explained in detail. Okay. Any more questions? All right. So that's it from my side. But wait, there's another session coming up next where we'll have Ishan Tandon talk about mechanical design, and it will be followed by a session on automation. So do stay tuned to that and see you around hopefully soon in the mini projects. Okay, that's it from my side. Thank you.
Okay, hello everyone. I'm Ishan Tandon. I'm in second year and mechanical branch. And today I'll be going over the basics of what is mechanical design and how is it related to robotics. So by the end of the session, you'll probably have a good idea of what we do in terms of robotics and mechanical, and if you find it interesting or not. We'll be also looking at a few examples of what we do in robotics. I'll give you a brief introduction of a variety of things, and at the end of the session, we'll have a short Q&A session where you can ask anything that you have doubts in, and I'll also share a few resources for you to get started if you find this interesting. Right, so let's move on. First up, we have the overview, which is what is mechanical design, how is it related to robotics, and how to get started. So, in terms of what is mechanical design, uh, when we look at specifically in terms of robotics, in mechanical design, you'll be dealing with the physical makeup of the robot, how it looks like, what the shape is, what features it has, and stuff like that. Then another thing would be the material selection, which is also really important. It depends upon how you want to manufacture things. If you want to 3D print, what type of material would you use, and stuff like that. Next would be joints. And whenever we have a robot, let's say we have a robotic arm, we always have joints between two links. If you have, let's say, your arm, your shoulder, and your elbow is a joint. So, what type of joints do we use? What are speed reducers? And what type of motors do we combine with these joints to get the required motion? Next would be kinematics and mechanisms, where we look at I'll give more details later on during this presentation about that. Next, we have testing and manufacturing. So I would argue that manufacturing is the most exciting part of the whole process, where you actually get to feel in your hand what you've manufactured, and you get to see it work in real life. But testing, which comes before that, is really important as well, because last thing we want is to like design something. Let's say it's groundbreaking, but we can't really manufacture it in real life. So it's important to have a look at testing and manufacturing in like a lot detail. Uh, Right, and at the end, I'll also show you a few facilities that we have on campus regarding manufacturing, like 3D printing, the workshop, the sandbox, which is the fabrication lab that we have. Right, so starting with structures. So let's take an example of a robotic arm. So whenever we want to design something, we first put down a set of requirements. These requirements could be something like a payload capacity. Let's say we want to pick up a weight of 5 kgs and we want to put it from point A to point B. So these are the test set of requirements. And when we design something, we keep these requirements in mind and design a structure that best suits these requirements. So let's say we have this requirement of picking and placing. We need a robot that has a sufficient workspace. So workspace is the whole region where the robot can reach. So if you're putting objects from point A to point B, the workspace needs to cover at least the point A and point B. And if you want to, it depending on how fast you want to pick and place, the weight of the arm, the moment of inertia, everything matters. So during the design process, you need to be careful of what these things are, and you want to design something that works the best. And another thing that's very upcoming is the topology optimization and generative design. If you have seen like pictures of generative design, they look very funky, and this is a good example of what it is actually about. So in topology optimization, as I mentioned, we want to reduce the weight. We want to still satisfy the requirements of loads. We don't want it to break, but at the same time be light as well. So topology optimization helps us with that. We input the basic geometry that we have. We input the type of constraints we have, the loads we have, and the computer helps us to identify places where we can remove the material and where we need to keep the material so that the strength is not compromised. So this is how the process goes on. We have a starting part, we remove some material, we add in the critical components, and then we end up with the final funky looking design. Right. Next, we have joints. So joints are very critical in terms of robotics. And before going into joints, I'll introduce you briefly to what speed reducers are. So let's take an example of a robotic arm again. You have a robotic arm and you want to add a motor on a joint to actually move the arm, but you can't directly couple the motor to the arm in most scenarios because we have a very high payload capacity, and so we require a lot of torque. But motors, on the other hand, are very good with speed, but generally not provide a lot of torque. So speed reducers help us to mitigate this problem. So we add a speed reducer right after the motor to reduce the speed but increase the torque. So I've given a few examples of the common speed reducers that we find, which is a cycloidal speed reducer, a harmonic speed reducer, and a planetary speed reducer. And to look at an application, I've given an example of MIT Cheetah. This is a robot made by MIT, and if we focus on the shoulder joint here, we have a cylindrical looking shape. So this comprises of basically the motor that they've used, which is a brushless DC motor, and I'll come to that later in the PPT. And they've coupled it with a planetary gearbox. So this is how we get to increase our torque and make a joint that is actually useful. Right. So if you want to look at the details of these things in detail, we'll provide resources at the end. So you don't need to worry about how they work at the moment. All you need to know about is that what they do. Right. So motors go hand in hand with these joints. Whenever we have a joint, we obviously have a motor going with it. So it's important to know what different types of motors are and how do they work. So if you have a specific scenario, you need to be able to decide what type of motors to use because you have a variety of options. So on the left hand side, we have the DC motors, and I'm pretty sure everyone has seen a DC motor in their life at least once. They're everywhere around you. Your computers, your microwaves, everything. And so DC motors are simple motors which uses brushes and permanent magnets and coils to rotate, which give you a constant rotation. On the other hand, steppers are a special kind of motors that instead of rotating in constant velocity, they move in steps. So this is very useful in certain scenarios. So if you want to have very precise stepping motion, steppers can give you that. So if you look at this GIF at the bottom, it shows you we have four separate coils around the edges, and in the middle we have a magnetic rotor. So whenever one coil is magnetized, the magnet follows that direction. And if you keep a coil magnetized and energized, the magnet will stay in that position. So steppers are great at moving in these discrete steps and also holding their position and giving us a lot of torque. So a lot of robotic arms utilize steppers because if you want to pick up something, a lot of times you want to hold it in place. So steppers are great for that. On the right hand side, we have the BLDC's motor, which is a brushless DC motor. And the construction of this motor is very similar to a stepper motor, but the practical working is very different. So they again have these coils and a magnetic rotor, but instead of moving in steps like a stepper, these BLDCs move in a constant rotation. So if you've seen drones generally utilize BLDCs. They're very efficient and they give you very high velocities as well. So BLDCs are generally better than DC motors in most scenarios and more efficient. In 3D printers, I'll give you an example. We use generally stepper motors because we want very precise motion and it's generally in steps. And BLDCs, as I said, are used in all sort of applications. Like if you have a computer, the CPU fan has a BLDC motor. And DC motor, we all know what it is. I'll also briefly tell you a bit about servos. So servo is basically a combination of a DC motor or a BLDC motor along with a sensor and a feedback loop. So to give an example, let's say you're walking in a park, and if you're, let's say, a stepper motor, your eyes are closed. You can't see what's around you. I'll tell you to move 10 steps forward, 10 steps back, one step left, one step right, but you won't really know in space where you actually are. You'll only know the relative position. So steppers and all sort of motors are like that. But servo is like you have that person, it can move whatever way it wants to, but you also give him a set of eyes. Now it knows where it exactly is, where it's positioned. You can tell him to go stand right next to that post. That's how servos work. So they can be DC motors plus a feedback loop, or a BLDC motor plus a feedback loop. Right. Moving on. Next up, we have mechanisms and kinematics. So in brief, mechanisms and kinematics are used whenever we have a robotic arm. We want to figure out so end effector is something, the final point in the robotic arm, if where you attach the gripper. So where that the gripper can reach in the physical space, how would it move around when, let's say, when you move the first arm, the shoulder joint, let's say, how is the end effector moving? When you move the elbow joint, how is the end effector moving? We have forward and inverse kinematics under this domain. So to briefly go over forward and inverse kinematics, so let's say you have a robotic arm again. I'll go back to the previous slide. Yeah, let's say we have this robotic arm. We have one joint over here and one joint over here. So and this is, let's say, the end effector. So forward kinematics would be key. Let's say you have the angle of the first joint, you have the angle of the second joint. So how would the final position be? Angle 1 plus angle 2, what is the output of that? So this is forward kinematics. You're moving, starting from the base and moving forward. Inverse kinematics is something completely opposite. You know where the final position needs to be, you know where the end effector needs to be, and you want to calculate what the joint 1 and the joint 2 angles should be. So they have a variety of different applications and different scenarios. You need both of them. So this is something you learn later on. One thing I'll also like to point out here is that if you look at this motor is the one driving this joint. So this motor drives this joint and moves this second link up and down. Link is basically this whole structure, nothing else. So this moves up and down, but it's instead of placing it over here and simplifying the design, we've placed it at the bottom near the first joint. So this is not by accident. It's very like a well thought of design. So this reduces the amount of torque we have at the joint 1. So if the motor is close to the joint, the axis of revolution, we have a lower torque. And also when we are actually rotating this joint, we have a low moment of inertia. So it can move faster, and like it has more strength as well to spare, because it's having to spend less of its energy holding up its own weight. So these type of small decisions on what mechanical design is all about, you apply your knowledge and try to get a best suitable design. Right. So in the mechanism kinematics, I'll also show you this GIF, which is the clan mechanism, which was made in the 2020 Quark. So this was made by our seniors when they were in their first year, and when the campus was actually offline. So this clan mechanism basically utilizes this whole kinematic diagram that we see on the right hand side, where we have an input as a circular motion, and the output is what we're getting by this shape. So if you follow this point, the last point, you can see that the underside is almost flat, while the upper side is whatever motion, we don't care about that. But because the underside is flat, this can very well mimic a walking motion. So when you're walking, your leg stays flat on the ground and moves back. So if you multiply this design, like let's say we put 1, 2, 3, 4, 5, 6, 7, 8 of these clan mechanisms on this robot and drive them together, but out of phase, we'll always have one of the foot on the ground, and it will help us walk forward. So this is an example of a very simple robot using that we made using kinematics. On the top, we have an example of what a workspace looks like. So as I mentioned earlier, a workspace is the region which the robot can actually cover. So this, if you have this example at the top where we have link one and link two, and the output is the end effector is placed at the second link's end. So when we look at the all possible positions of this end effector, we get a shape something like this. And on the right hand side, we have a MATLAB program that we wrote just to figure out what the shape would be if we have specified the length and the constraints of the whole kinematic mechanism. Okay, next up we have wheels. So wheels I'll give you an example of caster wheels first. So caster wheels are like wheels which are not powered. It is just a idler wheel that we place in situations where we just want to support some weight and also move in all sort of directions. So let's say you have a robot which has two wheels on the front, but the backside is touching the ground. It's like dragging along. We can add a caster wheel at the back, which will support the weight but also let it move in all directions. So what's special about caster wheels is that the wheel is offset from the vertical axis. So you must have seen these in shopping carts and all, where in whatever direction you start to move, the wheels align with that direction because of unbalanced forces and torques. So this is useful when you just want to add some idler wheel. At the top, we have wheels that are actually powered and let us move in a variety of directions. So these are called omni wheels. And by a special combination, by specially arranging these wheels in a specific shape, we can achieve motion that is not really possible with conventional wheels. If you look at a car, it can go forward and backwards and turn in a specific radius. But with omni wheels, if you look at this example in the trotbot, we have four of them placed at all sides and in a radially outwards direction. So let's say this wheel and this wheel is moving forward. This and the back wheel will drag on the ground, but because we have smaller wheels on the major wheel as well, it won't like create a lot of friction. It will smoothly drag. So you can move forward, backward this direction, and you can also move in the perpendicular direction. So it's like moving forward, backward, left, and right as well. And we can also move around rotate around the vertical axis if you move all of them in one particular direction. So this gives us a lot of flexibility on the way we want to move. And if you want to traverse a very complicated, very tight space, let's say a maze or something. Uh, this is also an example of an omni wheel. It's a bit different than this, but the purpose is the same, where you want to move in forward, backwards, left, and right directions all at once. Um, the continuous track is very obvious. It's like the ones that we have on tanks. So this can help you traverse regions that are like very bumpy or have gaps in them. So this has a continuous track that goes around and round, and this drum that you see is the one driving this whole track using small extrusions that are there on the underside. Then last up, we have manufacturing. So manufacturing is the like as I already mentioned, it's the most exciting part when you actually get to make things, and it's a lot of fun to actually work in the workshop and or 3D print something, or go into the sandbox lab and spend the whole day there just making something. So I'll give you an example of what all stuff we have on campus to manufacture stuff. On the left, we have the image of a workshop. So this is the workshop that we have on campus. It has a like a multitude of machines available to you for different type of jobs. So if you want to work with, if you plan to work with metals, if there's any metallic part that you have to manufacture, workshop is a place you'll probably go to. So in the workshop, we have the lathe machine, which is used for circular parts. We have the milling machine, which is used for making grooves or cutting specific shapes, cutting rectangular blocks or something like that. Drilling is when we want to make holes. So we want to through hole or something to put a screw into or something like that. And a five-axis CNC is a it's like a milling machine and a lathe machine. So it's like a combination of a lot of machines, and you can produce a variety of parts by inputting the specific geometry that you want. The structure, how it'll make the whole thing, is decided by the machine. Um, and on the right hand side, we have the sandbox fabrication lab, and this is again a place where you can have access to things like laser cutters, 3D printers, plasma cutters, and we also have a lot of tools available. And we also have electronic components like oscilloscopes. And all of this is available to you if you have a project in mind and you want to test out or prototype or actually make the final thing. Uh, then in the middle, we have the 3D printing as an example. So this is one of the major ways we manufacture our things, because we don't really manufacture it on a very big scale. At small scales, 3D printing is generally sufficient for us. And 3D printing allows us to produce a variety of shapes of whatever we can think of. And it's very versatile and very fast. So if you have something in mind today, you can manufacture it today or tomorrow itself. Then although like 3D printing is very famous and like it gives you a lot of possibilities, even it has some limitations. We look at it some other time, but 3D printing is not perfect in any way. All right, so that's all for today. So if you find this interesting, if you want to know more about what mechanical design is, and if you want to know the details of how we work and what are concepts, if you want to learn any concepts in detail and everything, you can go to this QR code, as Atharv mentioned as well. You'll find resources here for the commonly for common topics in all three domains: the mechanical, electronics, and automation. And these are a few specific links for the handbook, the QSCP material, as I've mentioned, and the mini projects is the something that we'll be releasing soon. So stay tuned for that. All of these links are also available in this QR code. So this is all you need. So take a screenshot or something for this. Then I'll move on. I'll wait for 5 seconds. All right. Right. So coming towards the end, I'm sure you must have a lot of questions. If you have anything, just type it on chat. I'll have a look and try to answer all of them. Feel free to type out anything that you have. And also, like, don't be scared with the amount of terms or different concepts that we introduced today. It's completely fine if you don't understand them. And even I started out from scratch. I didn't know any of this from before. So you'll be learning all of this as you go on through the projects, as you go, as we share resources, as you go through them. So don't be scared at all. If you find any of this interesting, that's all we need. So show interest, and you'll get into ERC and have get to work with a lot of things. Okay, so are the softwares provided by the college? So for CAD, we'll probably start with Fusion 360, and that is something that's available for free with your education bits account. So you don't need to pay for any of that. And later on, when we move on to SolidWorks or other softwares, we'll give you the student version for all of them. You never have to pay for any software. So do we have to master MATLAB for mechanical design? So no, like it's something like it's useful for simulations in a lot of scenarios. If you have so you can think of MATLAB in terms of mechanical like a fancy calculator. So you can do a lot of math in that. You can plot things. As I showed you a plot of this workspace, that black thing. You can do stuff like that, and it's very vast. So don't be scared to like learn MATLAB. It's not very difficult, and we'll give you a step-by-step process as how to go with that. It's not something that's necessary. Don't worry about it. So okay, so one question is, what do you recommend to get started? What should we begin learning? So at the start, I'll say start learning CAD. CAD is something that will help you all along to let's say you have a design in mind. So you put down on paper the basic design that you want. You sketch something out, and then you iterate it over and over. Rarely does the first design go up to the last design, and that's generally not what you manufacture. So, but at the end, when you have a design in mind and when you want to finally manufacture something, you'll need CAD to put it in a like a 3D model where you can actually go on to manufacture it either using 3D printing or some other fabrication method like using metals, the lathe, CNC, as I mentioned. So 3D print, the CAD design is a tool that's useful all along, and it's a basic requirement, you can say. So I've shared the resources again in the QR code. I'll go back to it again. I have mentioned a few resources to learn Fusion 360. It's a YouTube tutorial, and that's what I used when I started learning as well. So it has a couple of videos. Just go through that and keep practicing at the moment. Rest, when we start with the mini projects, you'll be introduced with a lot more topics, and we'll again guide you throughout the way as how to go about learning all of them. So never feel scared. Just keep participating. We again have a question where it says regarding the funds and the projects. So you don't need to worry about funds and all at the moment. So it's something for another time. It's not student funded. Another question we have is, what type of motors are required for flight? So I mentioned earlier that BLDC's motors are used for. We'll go back. Yeah, BLDC, the motors are used for if you have fixed wing aircrafts or if you have drones. BLDC is what we generally use. Steppers are used when we have a very precise application, as I mentioned, 3D printing or a robotic arm or something. BLDCs give you a continuous motion, and steppers give you a discrete steps. Okay, if that's all, okay, there's one more question, I think. Okay, what does sandbox mean? So, okay, so sandbox is like the fabrication lab that we have. I mentioned a few facilities that we have available there. So let's say someone mentioned what type of motors are used for flight. So let's say you're manufacturing a drone or something, and you want to manufacture the frame. So you'll probably go to Sandbox Lab, you'll use the laser cutters to manufacture the flame, or if you want to make it out of metal or something, you might go to the workshop. And let's say you want to have a project in mind and you want to 3D print something. Once you get approval, you'll get the access to this 3D printing tools that are available there. You'll get the filament from there and everything. We also have a lot of mechanical tools there, screwdrivers, wrenches, and like a variety of things. So it's like whenever you want to manufacture something, Sandbox is probably where you'll go. Right. Anything else? Okay, so we'll end the mechanical design session, and we'll next up we have automation, which will be presented to you by Dhruv. So I'll hand over to Dhruv now.
Hello everyone, I am Dhruv Poddar and I will be taking this session on automation. So let's start. Um, so in this session, I will be telling you about some of the recent advances in robotics, the role of automation in robotics, how to get started with some automation processes, and some of the resources that you might need to get started. Um, just a second. Mm, Yeah. So let's talk about some recent advances in robotics. So in the past few decades, robots have become more efficient and capable. We used to have like robots, like basic human arms, which are controlled like by remotes and radio software. But nowadays, these are pretty much automated and can build products as complex as a car part to and sometimes even do heart surgeries. Nowadays, we have Roombas which can navigate and clean entire houses on their own. We have drones which previously had to be flown around manually using remote control, but now they can follow you around and perform complex aerial acrobatics on their own. Robots have become more reliable and precise, and like all of this is given to us by automation. So how does automation come into robotics? Everyone, in the last two sessions, you learned about mechanical and electronics. So if you think about a robot as a human being, the mechanical and electronics part form the body of the robot, and automation forms the brain. It makes the robot sense its surroundings, navigate, and perform tasks in an environment all using a very simple set of instructions and a CPU. Automation also helps in making the robot less dependent on human control, which is something that is very important nowadays because of issues I will speak of in the future. So automation has three subdivisions: perception, control, and planning. Let's start with perception. Humans experience their surroundings using their sense organs. The stimuli we get using our eyes, nose, and ears gives us a general idea of our surrounding and helps us find ourselves in our surroundings and get a general idea of where other objects are located. You can think of this as a map, like a map which is giving you a complete idea of everything in your surroundings. Robot does the same using sensors such as LiDARs, IMUs, and cameras, which allow it to quote unquote see its environment and give it a map of the surroundings. So here we have a simulation that we have built up for you. It's a simulation of a very famous algorithm known as G mapping. What this does is like, as you can see, here is a simulation, and here on the left side is what the robot sees. The small green dots you can see is where the algorithm thinks the robot is, and on the right you can see where the robot actually is. This is all done using a simulator on called Gazebo and RViz. And as you see, as the robot moves around, it starts to see different parts, which are signified by the grayed out areas. Like in the right side, you can see the pillars, which are slowly becoming visible as the robot comes near them. So now the most like planning. Planning is finding a feasible path from one state to another in an environment. It is basically the robot deciding where it should go and how it should go there. So it is a very complex algorithm. It is a set of very complex algorithms which are usually used to make robots navigate in their environments. And often, as a test, we use them to navigate a maze. Planning is not limited to maze navigation, though. In advanced robots, one must decide what actions to perform and the order in which one must do them, which also comes under planning. So here we have a model built by one of our club members, which, as you can see, the robot is navigating from one part of the maze to another. It sees that the red area is the destination, goes there and stops. Next, we have controls. So now that the robot has seen its environment and has its path planned out, we need to execute that path. This is where controls come in. Most of the sensors and algorithms used in robots are not absolute. They have some sort of an error associated with them. For example, if you imagine a car driving on a road, now because of some issue in the car might drift to one side, or it might change its speed. To correct for these errors, we employ different controllers which take into account the current state of the system, the destination of the system, and change the inputs to make sure that the robot or the system is going in its desired direction. In the car example, this would be the human who will steer the car accordingly. So let's talk about how to get started with automation. For everyone starting robotics who doesn't have any experience with coding, I would suggest that you start learning Python. It's a very basic language and is a great starter for new people. Then the next step would obviously be choosing a domain from the three that I just talked about: controls, perception, and planning. And the next step, which is the most important, do a Google search. Doing a Google search is the best and easiest way to find any information that you want, and it is like the most convenient place. So let's talk about some advanced skills that we use here in ERC that often that you saw in the previous slides. So for programming languages, we have C, C++, Python, and often MATLAB and Simulink. The OS and development tools, while most people use Windows, robotics tasks need to be done on Linux for reasons which I'll explain. So Linux and the terminal. The terminal is a very important tool that is instead of being graphical, it gives you a list of everything that is happening. And that is very great when you want to debug or let's say make some changes in your robot. Next thing, Git. So Git is used for version control. When you work with multiple people and collaborate on tasks, it is very difficult to get a hang of what this guy did and what this guy did and what the other guy did. So Git is used for that, as it gives you a visual, a depiction of the, let's say, a depiction of the tree in the way, like a depiction of the inputs and outputs provided by the different users. For the next thing, we have some softwares that we use, ROS, which stands for Robotics Operating System, and Gazebo. So in the last few slides, you saw a few simulations that we had done on ROS. This one, the maze navigation one, and the perception one. These were all done using ROS, and ROS provides us as a suitable backend that can help us in organizing our tasks and provides an interface for you to link your software and hardware. So some resources. So getting started, I would like everyone to start out with the ERC handbook available on our website. It is a exhaustive and extensive list of resources that you will need to complete to get started with any of the three verticals, be it mech, automation, or electronics. For Python, I would suggest you to do the Corey, Schaefer, and Sendex Python tutorials. And if you want anything from the club, we have some mini projects planned for you people, which will be starting in the next few days. You can scan this QR code for some of a list of resources available on the Notion page. So yeah, I would be taking some questions now. So one question is, how is Python used for ERC stuff? So we use Python extensively in ERC for writing codes related to path planning, machine learning, artificial intelligence, and even for control systems. Basically, all the three domains that I listed above, perception, control, and planning, all of them have some sense of Python code in them. Most of the algorithms are also listed in Python. Reason being, it is a very simple language and it makes you focus more on the algorithm or more on what you're writing instead of how to write. So one question is, how do I work on the activities that require Linux if my laptop only has Windows OS? So an OS that sits on your laptop's hard disk is usually Windows. For most people, it is Windows. But what we do is we have two ways. We can either use a virtual machine or we can dual boot. A virtual machine is an application that runs on top of your Windows and will provide you with a Ubuntu interface or a Linux interface. And dual boot is where you partition your drive and boot two operating systems on the same drive. When you boot up your laptop, it gives you a choice as to whether you want to boot into Windows or into Linux. The second option is obviously preferred because it actually allows you to use your system's resources to their complete potential. But for those who have some problems doing a dual boot, Windows making a virtual machine is obviously a great idea. Another alternative to doing a dual boot is using WSL, which is like a simple application that that you can download using a Windows Store. Some of you can check it right now in the Windows Store. It is basically just a command line that is inbuilt into your Windows. It's like a very simple interface, but it is less recommended for robotics use cases because it does not have some GUIs that we might need. Any other questions? So how do I work on a laptop? That's done. So for Mac people, I don't know if you can dual boot using your Mac, but you obviously have the option of using a virtual machine. Not sure if dual booting is possible. Is it advisable for trying VS Code for coding? So VS Code is just an IDE for all practical purposes. You might as well code on the default text editor. It doesn't matter. But obviously, VS Code has some perks and features such as extensions and support for various languages that help us. So yeah, VS Code is a good way to start. Does Gazebo need a tutorial too like Python and C++? So Gazebo comes installed with the package that I just called, that is ROS, and ROS is a very advanced framework. And yes, you will need a tutorial for ROS, but you will probably need to learn basics of Python and some other stuff first. Gazebo is a simulation environment and as such does not require a tutorial. It is pretty self-explanatory. Like once you open the app, you can start understanding what it does. Can you explain the induction process and give some tips and tricks? So the induction process, as someone has told in the chat, will be you will be starting out with the mini projects, which will be starting from 4th of February. These projects will be approximately 1.5 month long, where you'll learn some of the basics of what we do here. And as the process goes on, you will be introduced to many important concepts, and based on which we will take an interview at the end after the mini projects are over. And as for tips and tricks, all I can say is take part in the activities of the club and show enthusiasm. Can we use PyCharm for writing Python programs? So PyCharm is a very, let's say, beginner-friendly IDE. It is used for writing basic Python programs, and does not support that many of the features that we need. You can start out with PyCharm, of course, but somewhere along the way, I would recommend that you can switch to VS Code or any other better text editor. PyCharm is an IDE, which stands for an integration development environment, and it only supports that one language. Whereas VS Code is a text editor, so you can edit basically anything on it. So guys, you're also free to ask any questions from any of the other sessions as well, electronics and mechanical. So yeah. Is Eclipse fine? I don't know much about Eclipse. I think it's an IDE for Java, not completely sure, but yeah, maybe someone can look that up. What all stuff do we need to learn from mini projects? So for the mini projects, since they are obviously meant for firsties, we have literally no prerequisite. All you need is a will to learn and an interest. We have mini projects on topics from all of the 3 domains. I think we have 2 for each domain. You can choose which one you want and get started on the 4th of February. So yeah. All of the learning will be done during the mini projects. It's preferable if you start learning early, but I don't think it's required. So I guess there are no questions, so I'll just end. Last announcement that I would like to tell you is that we will be having other mini projects starting from the Friday, which is on the 4th of Feb. And yeah, the information will be shared to you on the groups. I hope most of you are on the ERC groups. So yeah. Thank you. Another question that has popped up is, do we need to get into core of Python and C++ for further projects? If by core you mean like really advanced Python stuff, then not as of now. But I think somewhere down the line you probably will be using that. But yeah, matlab, not too advanced and not too simple either. I guess that's all. So I'll be ending the talk now.